Now, let's recall. I mean, in theory, of course, we never use this expression as just a theoretical expression because usually in population, we never know mu, and so far we cannot compute it because we don't have access to the whole population. So in theory, you can compute population average by taking a sum of all your values and divide it to the number of these values, right? And then actually for computing the sample mean, we do the same. We simply take all values, take a sum of all values, and then divide to n, right? So that's the way to compute mean. The only difference is that in case of a sample, the number of values, all this x, is limited by a sample size. Now let's talk a little bit more about this mean of your sample. Well, you remember that if we assume that values are normally distributed, then we can write it like this, right? So x, it's your particular value, for example, sugar of one single apple from a large garden. So it's distributed normally. It means that it has these two parameters, mu and sigma. Mu is the center of this distribution. It's a population mean. Sigma gives you variability. It's a population standard deviation. And the z, it's a z-score. So it tells you that it's a random value, a normally distributed random value. It follows standardized normal distribution. And in 68.3% of these cases, z-score is limited by plus minus 1. In 95.5% of the cases, it's limited by plus minus 2, and so on and so forth. So this is what we know so far. Now, look, we want to calculate average of several apples, right? But we know that sugar content in every apple follows this expression, right? So we know that sugar content in the first apple, it's a sum of, first of all, average of population, which we don't know, and then a random value from standardized normal distribution times the standard deviation of this population. Then the second apple is the same, and the third apple is the same. The only difference why actually apples have different sugar content in this Z1, Z2, Z3, because they are random numbers, they vary randomly within given limits, so that's why we have this random variation of sugar content. And we know that the reason for that is many different external factors, and when influence of these external factors sums up, then you see it as a random effect. Right? However, let's limit our sample to 3 and let's compute average of these 3 values. So average of these 3 values we compute by taking a sum of these 3 values and divide to 3. So that's easy. However, look, if you take a sum of this part, you will have 3 mu, right? Then if you divide it to 3, you will get mu. Yeah. Then if you have sum of this part, you will have z1 plus z2 plus z3 sigma. You see, because you have sigma for every term here, I can just put it outside the parentheses and then divide it to 3, right? So this is it. So the average of a sample of size 3 looks like this. So what it means, look at this one. It's very similar to this expression, right? You also have mu, you also have sigma, but instead of z, you have a new random number, which is a sum of 3 random numbers divided to 3. So it's average of z-score, average of 3 z-score. So what it means, if this is a random number, it means that average of your sample also a random number. So every time you take a new sample, you will get a new average, although the samples came from the same population. So average of your samples also a random number. While mu and sigma are fixed, so the population parameters are fixed, the statistics of your sample that correspond to these parameters, they are not fixed, they're random. And every time you take a new sample, you will get a new statistic. So that kind of complicates things, but let's figure this out. First of all, let me generalize this to any sample size. So before I use sample size of 3, now I can do the same for sample size of n, where n can be any number. 5, 10, 30, doesn't matter, right? The idea is the same. So sugar content in every apple can be described by this if it follows normal distribution. And then it means that when we take an average, we take a sum of x values. But on the other hand, it means it's a sum of mu values, these ones, and then it's a sum of these values. And then we simply can use the same mathematics to derive this expression. Right? So this is a random number. So the average of your sample varies randomly around average of your population, and this is the magnitude of this variation. So let's discuss this magnitude of this variation. So average of your sample is a random value which is distributed around average of your population. It follows normal distribution. You can see a very clear link, except instead of z, just a single z here, you have an average z. But if you have something that follows normal distribution, some of this will also follow normal distribution. So from that case, we can be sure that average follows normal distribution in this case. And then we also can see the larger sample sizes, the closer m will be to mu, right? Why? Because if sample size is large, then this will be close to 0, because you remember that the true average of z-scores is 0. And therefore, this will eliminate this term, and then m will be also closer to mu, right? And we know that m is equal to mu only if your sample size is infinite, or at least if your sample size is equal to the population size. So if you compute this for the whole population. So these are preliminary conclusions. Now let's investigate this part. Now look, if you take z-score, if you take distribution of z-scores, we know that average of this distribution is 0, and variance and standard deviation is 1, right? So that's what we call standardized distribution. But what if we consider distribution of sum of several z distributions, right? So take, for example, I don't know, population of 1 million z-scores, then another population of 1 million z-scores, then another population of 1 million z-scores, and take a sum of these three populations. So what will be the average of this sum? Well, apparently average, we compute average as a sum of values, right? So it means that if you have a population z1, which is, for example, consists of, I don't know, 1 billion different z-scores, like z11, z12, and so on and so forth, z1n, right? So you have n, very, very large number, it's a population. Then if you take a sum of this, that will be the, and divide to, let's say, let me use this, sum of z1i divided to n, right? That will give you the average of z1, right? Then the same, if you take z2, you have another z21, and so on and so forth. So another population, which follows the same distribution. And then if you take a sum of these, divided to n, that will give you, this sum will give you the average of z2, and so on and so forth. But if you take an average of sum of that, it will be the same as average of every single population, right? Because sum is commutative, then you can easily derive this, right? So the average of this population, where you have n single populations of z-scores, it's the same as the sum of these average values for every population. And that gives you 0, because sum of this is 0, sum of this is 0, sum of this is 0. Okay. So now we know that if we consider a distribution of sum of z-scores, then the average of this distribution will be also 0. So it's the same. Now let's think about variance of z-scores. In this case, it's a little bit more difficult to derive, but you can, in this case, just trust me, or you can find the derivation in Google if you want, that the variance of this sum of z-scores, of sum of n populations of z-scores, it's the same as sum of their individual variances. So that can be proven. But remember that the variance of one single population of z-score is 1. The second also 1. The third is also 1. So it means that the variance of sum of n z-scores distributions is n. And if variance is n, it means the standard deviation is square root of n. Well, I told you that I don't want to show you how to derive it, but I can actually prove it by simulations, right? Kind of proof. Let me show you how I can do that. So this is our code where I take a population of z-scores. It's actually a sample, of course, but you can see the sample size is very large. So we have, like you can see, 7 zeros, so it's 10 million values. So I take 10 million z values randomly, and then I compute average. And then you can see that average is almost 0. That's what we expect, because we know it already from block number 1. If I compute a variance we expect to be 1, right? So that's also we know. And if I compute variance, you can see indeed I got 1. So indeed, for my experimental values based on this simulation, they prove this, at least this part, right? Now let's prove this part, how we can do that. Well, in this case, I take 3 subpopulation, let's call it 3 large samples. Every sample has the same size as 10 million values. So we have Z1, Z2, Z3. In every In Z1 we have 10 million values, in Z2 we have 10 million values, in Z3 we have 10 million values. And then I compute average of their sum. So this is exactly this one, right? And you can see that the average of their sum is indeed 0, what we expected. Now I compute the variance of this sum. And look, variance is 3. Of course, it's not exactly 3 because my sample, in this case, I have like 10 million values. It's not infinite. But you can see if you round it even to 1 decimal, we get 3, right? This kind of an evidence that our theoretical expectations are correct. So we know that if we take a sum of z-scores, the average will be 0, the variance will be n, and therefore the standard deviation will be square root of n. So that's what we know so far. Now, another way to prove it is to make a distribution, right? So in this case, you can see I have a single big, very large sample of z-scores. If I make a histogram, you can see indeed the most of the values, they lie between plus minus 2. We know that it's 95.5% of the values, right? If I do the same for, in this case, you can see I have a sum of 4 z-scores, right? 4 samples, 4 large samples, or you can think about populations as well in this case. So you can see that if we find the same pattern in the histogram, and look, this is where the pattern is, right? So this is exactly the same pattern. You can see these 3 bars here, these 3 bars here, they equal to these 3 bars and these 3 bars, right? Then you can see what is here. So you have 0 here and minus 5 here. So here you have exactly minus 4, and here you have exactly 4. Here you have minus 2, and here you have 2. So you can see the interval gets twice larger. Why it's twice larger? Because in this case, n is equal to 4, and it means that the standard deviation of z1 plus z2 plus z3 and plus z4 will be a square root of 4, which is 2. So standard deviation, remember here, the standard deviation is 1, right? So standard deviation is twice larger, and therefore the interval between plus minus 2 standard deviations is also twice larger. So that's another kind of, it's not proof, of course, because it's not a strong mathematical proof, but it's kind of an evidence based on computer simulations that what we derived so far is correct. Okay, good. Now we have this knowledge, so we know that this is average of sum of nz z distributions, and this is standard deviation of sum of nz distributions. But what that means? It means we can do the following. Let's call this sum as y, like this, right? But it means that we can write the following. So y, it's a normally distributed value that came from distribution where you have mu plus z sigma, right? And now z is single. Mu is 0. Sigma is square root of n. So we can write it like this. It's z times square root of n. So instead of this, we can write this. That will simplify because we will get rid of sum. Let's do that. So this is it. So this is the expression. So you can see that I just took this sum, this one, and I replaced sum with z times square root of n, and this is how I got it. This is where the sum is. So this one is z1 plus z2 plus and so on and so forth plus zn, right? But what it gives us, now we can simplify this. First of all, you can see we have n in denominator and square root of n in nominator. But we know that n, it's like square root of n multiplied to square root of n, right? Square root of n squared. So I can write it like this. Now you can see this cancels out, right? So we have z divided to square root of n. And let me just rearrange this. So instead of sigma z divided to square root of n, I will write it like z sigma divided to square root of n, because multiplication is also commutative. I can do this, right? And that gives us the final expression for average of your sample. So average of your sample is normally distributed random value. It varies around average of your population. And this is the variation. This is the standard deviation of this variation of this of the average values. You can see it's not sigma. It's sigma divided to square root of n. Okay. So the result, what you see here, it's a part of what is called central limit theorem. It can be proven, I will skip it, I'm not going to do that, but it can be proven that it's true not only for normally distributed populations. It's true for any population. Average of sample taken from any population will follow normal distribution with these parameters. Okay. So this part, it's a standard deviation of the average values. So it depends on two things. It depends on standard deviation of your population and sample size. Because now we have kind of two standard deviations. We have standard deviation of values and we have standard deviation of mean values. To avoid any confusion, we will use a special name for this standard deviation. It's called standard error. So when we say standard error in this course, it means it's a variation, it's a statistic that describes variation of statistic, of sample statistic. So standard error, in this particular case, it's a standard deviation of sample average, not of values, but of sample average. Okay. And this is just to compare, right? So when we talk about one single value, for example, apple from a particular tree, or concentration of chemicals in one glass of water taken from a large lake, right? So in this case, if these values follow normal distribution, we describe it like this. We say, this is the random value taken from this population, this is population average, this is population standard deviation, and then we have z-score, which is, just a normally distributed random value, right? When we take a sample of size n, so now we have not just one single x, we have x1, x2, and so on and so forth, xn. It can be n apples from big garden. It can be n glasses of water from large lake, and so on and so forth. And then if we compute average of these n values, then this average of these n values, average of your sample, will also follow normal distribution. And it will also be random number. It will vary around population average. And this is the measure of this variation. So the analog of standard deviation here, for one single value, we have here a standard error, right, for average of n single values. Okay, so that's the main difference. So when we say standard deviation, we talk about values. When we say standard error, we talk about statistics, in this case about sample average. Okay. So this magnitude of variation, how far average of your sample can go from average of your population, we will call error margin. And you can see it's random value, right? So this is a fixed part. So this is fixed, it's standard error, right? But this part is random. This part is random. So it means that the distance between m and mu, let's say m is here and mu is here, right? So this distance, it's a random value. So sometimes m can be close to mu, sometimes m can be large from mu. You remember z-score, for example, in 68% of the values, in 68.3% of the cases, z-score goes from -1 to +1, right? So sometimes z-score is close to 0. In this case, this distance will be small. But sometimes z-score can be -1 +1 or -2 +2, even -3 +3 if we talk about 99.7% of these cases. In this case, this distance will be larger. Okay. So let me show you a couple of examples. So in this case, again, I have values, single values, and I have sample means. So what it means? It means that I took, in this case, you can see n is equal to 25. I took, let's say, 25 apples from the big garden, for example, and then I compute average of these 25 apples. Okay. And then I repeat it again. I repeat it many times. So I got a lot of samples. Every sample consists of 25 apples. And therefore, I got a lot of average values. And this is distribution of these average values. So this is distribution of average values, while this is distribution of single apple sugar content. Okay. Now you can see in this case, the sigma, the standard deviation of distribution, is 10. But in this case, if you look, it's much smaller, right? And then if you compute the standard deviation, you will find out this is 2. Why it's 2? Well, you remember that this is standard error, right? Standard error can be computed as the standard deviation of your sample, standard deviation of your population divided to square root of your sample size, right? So that gives you 10 divided to square root of 25. Square root of 25 is 5. 10 divided to 5, it's 2. So standard error is 2. So the bigger sample size is, the smaller this variation is. And therefore, the closer the m will be to mu, and therefore the more precise estimate you can make if you just compute a sample average This is another example. In this case, I have n equal to 100. You can see this distribution is even more narrow, right? Why? Because you remember that the variation of this distribution, the standard deviation of this distribution, which we call standard error, is 10 over square root of 100, which is 10 over 10, or equal to 1. So now it's twice smaller. So the larger sample sizes, the smaller uncertainty, the smaller distance between average of your sample and average of your population. Okay. This is just both cases to compare. You can see this is n equal to 25, this is n equal to 100. Standard deviation of your population is the same. I only changed sample size. Then you can see that this part, this variation, all possible m values for your sample, is twice smaller comparing to the case where you have sample size of 25. Okay. So these are main takeaways from the first video of this sequence. So average of your sample, always normally distributed. So average values, it can be proven mathematically, always follow normal distribution. And this is true also if populations are not normally distributed. I didn't prove it, but you can also find the mathematical proof yourself if you Google for central limit theorem. Okay. The average, the center of this distribution, it's the same as the center of the distribution of your value. So it's a population average mu. And the standard deviation of the distribution of means of your sample, we will call it standard error, and it can be computed by taking a standard deviation of your values and divide to square root of the sample size. So now we know how m and mu relate to each other. We know how big the distance can be between m and mu, and we know how to make it smaller. In the next video, we will talk about how to use this knowledge for practical purposes.